In this module, we'll look at simple models that help us understand vapor-liquid equilibrium. We've already been introduced to Raoult's law and the ideal conditions under which Raoult's law operates. Application of Raoult's law, however, requires us to know Pi sat at the temperature of application. However, for gases whose critical temperature is lower than the application temperature, Pi sat cannot be calculated. An example is air. Consider an air-water mixture. X water times P sat water is equal to Y water times P. So I'm able to write this equation for the water component. So assuming that liquid water is pure, I have P saturated water, so X is equal to 1. That's equal to Y water times P. Thus one can calculate the mole fraction of water vapor in air. However, if one needs to calculate the mole fraction of air in the liquid water, then Raoult's law cannot be applied, since P air saturated at 25 degrees centigrade does not exist. It is already past its critical temperature, so no pressure for vaporization exists. This is where Henry's law becomes useful. For species present in very dilute concentrations in the liquid phase, Henry's law states that partial pressure of that component in the vapor phase, is directly proportionate to its liquid phase mole fraction. So it states that the partial pressure of that component in the vapor phase, which is Yi times P, that's the partial pressure in the vapor phase, is proportional to its liquid phase mole fraction. Liquid phase mole fraction is Xi. The constant of this proportionality is Hi. Thus Yip is equal to Xi Hi, where Hi is the Henry's law constant for component I. Henry's law constants are experimentally determined and available. So for example, Henry's law constant of gases in water, here are a number of them, and they're expressed in bars. So we have at 25 degrees we have the Henry's law constant for air, helium, methane, and so on. So for example, using Henry's law, when there is 3 mole% water vapor in air, so Y air is equal to 0.97, and H air, the Henry's constant for air in water at this temperature, is 72950. So when there's 3% water vapor in air, Y water is equal to 0.03, Y air is equal to 0.97. So Xi is equal to Yip divided by Hi. P is equal to the atmospheric pressure, 1 bar. Yi is equal to 0.97. Hi is equal to 72950 bar. Hence the mole fraction of air in water is 110 per minus 5. So indeed it is extremely dilute. In addition to using Henry's law constant, we can also use an equilibrium ratio or a K value to describe the equilibrium concentrations between a liquid phase and a vapor phase. The tendency of a component to separate into equilibrium concentrations in the liquid and vapor phase is given by this equilibrium ratio K. So let's say I have a system, I have liquid here and vapor here. So if I have component I, the amount of I in the vapor phase and in the liquid phase, so how much of it is in the vapor phase and how much of it is in the liquid phase, this ratio is given by this equilibrium constant Ki. It is a measure of component favoring its presence in the vapor phase. When Ki is greater than 1, the component prefers the vapor phase. When Ki is less than 1, it prefers the liquid phase. So if I compare this relationship with Raoult's law, remember that Raoult's law was Yip is equal to Xi Pi sat, and hence Yi over Xi was equal to Pi sat over P. And so putting this equation right here, I have Ki is equal to Pi sat over P. Thus Ki can be calculated only as a function of pressure and temperature. Remember that P sat is a function of temperature, and it is independent of composition. Thus, where Raoult's law holds, this is quite useful. I know that the summation of Yi is equal to 1, and hence Ki Xi can be written as 1. Also, since the summation of Xi is equal to 1, Yi over Ki is also equal to 1. So remembering these relationships, I can again use this to calculate how a component would partition between the vapor phase and the liquid phase. Let's look at flash calculations. Consider this PXY diagram. Remember that this PXY diagram is for a specific temperature TA. Now consider a two-component system which is at this pressure. From this diagram we know that at a pressure more than the two-phase region, the system is in a liquid phase. All components are in a liquid phase. Now let's say that we take this system and bring the pressure down to this point here. This is the final pressure. So the system will be in equilibrium at this pressure and this temperature for which this PXY graph is drawn. And at that pressure, the equilibrium conditions will result in a two-phase system, a liquid phase whose composition is given right here, X1 liquid and X2 liquid, and a vapor phase from this dotted line here whose concentration will be given by, or mole fraction will be given by Y1 vapor and Y2 vapor. So this is the equilibrium condition. This process of suddenly reducing the pressure and causing a change in the phase of the system is called a flash. This is very useful in separations, so we will look at this a little more closely. A liquid that is at or above its bubble point pressure, this pressure here is the bubble point pressure for this composition right here, will partially vaporize when its pressure is reduced, forming a liquid and vapor phase in equilibrium. It will partially vaporize if its pressure is brought down here. If its pressure is brought down here, it will vaporize completely. This process of partial vaporization is called flashing, and of course we assume that there are no chemical reactions. We can calculate the equilibrium condition of flashing using the equilibrium coefficients that we have looked at, or the Raoult's law that we have looked at a little while ago. So for a total composition of fluid, we can calculate the equilibrium composition of liquid and vapor phase after the flash at a known temperature and pressure. Assume that there were 1 moles of initial fluid at composition Zi. In this particular case, we know that the fluid was in the liquid phase, but it is not necessary that we know that a priori maybe the fluid is in a liquid vapor phase right here, and we are bringing it down to the liquid vapor phase right here. So in that case, the initial equilibrium condition would be this and this, but when you lower it down here, its equilibrium conditions would be this and this. So it's going from a two-phase to another two-phase, but the compositions of the two phases are shifting. So that's why we assume an initial fluid composition Zi. We don't know the Zi. We do not know whether Zi is liquid, vapor, or both. Assuming that after flashing, there are L moles of liquid with composition Xi and V moles of vapor with composition Yi. Doing a total mass balance, we have L plus V is equal to 1. Since initially there was 1 mole of total fluid, the total liquid plus total vapor is equal to 1. Zi, the mole fraction of component I initially, is equal to Xi times L. So the mole fraction in the liquid phase times the total liquid plus YIV, the mole fraction of I in the vapor times total vapor for each component I. Putting this equation in here, I have Zi is equal to Xi 1 minus V plus YIV. Since Xi is equal to Yi over K, I get rid of Xi from this equation here, and I have Yi is equal to Zi Ki divided by 1 plus V Ki minus 1. Taking summation on the left hand and the right hand side of the equation, and since sigma of Yi is equal to 1, sigma of Yi is equal to 1, I have 1 is equal to this summation right here. I know Zi, I know the Ki's of each component. The only thing I do not know is V right here. So I can solve for V. It's a little complicated an equation because there are a number of terms in this summation. However, through iteration I can calculate V. Once I get the value of V, I can use this equation right here to get Yi. Once I get the value of Yi, I can calculate the value of Xi right here, and hence I know the equilibrium composition of the liquid and vapor stage.